a fantastic book. It's pretty thick, but it has pretty much everything you need. There is a little bit of magnetic point group and spin group and double group and stuff like that at the end. But most of it is about group theory applied to the degeneracy lifting and band structures and stuff like that. So very, very useful for us. So I'm really following step by step the first 4 chapters of this book. And I think it's actually quite useful, because then when you buy the book and you go through the book, you're going to find the same elements. Okay, I'm not inventing anything else. Just following. So I would assume that you guys are familiar with the point groups. I'm not going to talk about space groups here, just point groups. So you have different denominations, and depending where the culture of your physics department is, you might be using this kind of denomination or this kind of denomination. Here, again, I'm following very closely to the house, and I'm using this one. So you have all your lattice classes plus the point group. So I will not go through that again, because I think you have already heard about that a lot since the beginning of this school. And I would actually start with a few definitions. So again, in the House book, you have a first chapter that is really about mathematical definitions. The only thing we need to know is that if I take a point group of a material, any of it, you know that this material obeys a number of symmetries. And there can actually be many symmetries. You're going to see a few examples, including the famous D3 triangle that we saw yesterday with Oleg. And what is interesting is that we can classify those symmetries, because some of those symmetries actually look alike. Like a 3-4 rotation one way look very much like a 3-4 rotation the other way. Okay, so they may, depends actually the kind of symmetry you're considering, they may be so similar that we're going to put them in the same class. Okay. Well, it actually depends. So we'll see that in details, and then we can basically put those symmetries together and create what we call classes. And that's what we're going to start with right away. What is interesting is that those symmetries, so 3-4 rotation, mirror, whatever symmetry fits your crystal, they actually form a group, which means that when you are on a particular crystal and you apply rotation, then mirror, then rotation again, then inversion, and whatever symmetry the crystals has, then of course you take one point of the crystal, you apply all those symmetries, and you should have another point of the crystal again. Okay, of course you're not getting out of the crystal, otherwise it's not the symmetry of the crystal. So the fact that those symmetries basically talk with each other, that combining symmetries gives you another symmetry, it's actually equivalent. This is called a group. They form what is called a group. So there is mathematical definition behind the group. You have basically you take 2 elements of the group, so 2 symmetries, you combine them together, you can have another symmetry of the same crystal. Okay. So we will end up, we'll end up with, I don't know, crystals with 6 different symmetry operations, or 48 different symmetry operations. And each time you combine those symmetry operations, you will stay in the group of those 48 symmetry operations. Okay. So this is the first rule. Then there is the associativity law, which is quite formal, to be frank, but essentially you combine them, and I'm not going to talk about that because that's kind of obvious, in fact. There is always a unit element, which is the identity. And for every element of the group, there exists its inverse. Okay, you can rotate one way, you can rotate the other way. You can have a mirror. Well, actually, mirror is it's kind of obvious, right? You take a mirror, you apply the mirror once, you go from one place to the other, then you apply it again, come back to the original place. So the mirror is the inverse of itself. So for the hardcore theorists in the room, if these symmetries do not commute, then you have a non-Abelian group. But we're not doing that today. I have to learn that, so I'm not going to talk about it. No question. Okay, let me see. Now there is actually another definition that is again quite abstract but extremely useful, and that will allow us to create subgroups of those symmetries. And this definition is called the conjugation. So the conjugation, so the element B conjugate to A is by definition B equal x, A, x minus 1, where x is an arbitrary element of the group. So basically, what does it mean? It means that you have, let's say, take a group with different operations, okay, different symmetries. And actually, two symmetries of your group will be conjugate if you can find an element of the group such that you have this relation here. That it will be, I don't know, that's 1 and 4. Okay, where x is one of these elements. It could be the same, it could be something else, it doesn't matter. Okay. And what it means for us as physicists and not mathematicians, we even say experimental physicists, don't care about theory, it means that they basically look alike. I will give you some examples about that. Okay. We will see that with the rotations, for example. When you have a triangle with, let's say, 3 equivalent axes, rotating around one of the axes is equivalent to rotating around the other one. It's not the same thing, of course, because you're not exchanging the same points, but you actually do have this relation, because if you rotate your frame, well, then you will see that, let me take this guy here. Rotating along that is the same thing. It's not the same thing, but is equivalent as rotating around that. So it means that this rotation will be in the same class as this rotation. And of course, as the same class as this rotation also. Okay, so of course, it's not the same thing. That's why these guys are not equal, but they are related by this conjugation. And this is the only thing we care about. Okay. So let's take an example. Yeah, it's an evolutive presentation. I changed it yesterday when I saw that Oleg was actually talking about it. So, so we take our triangle. Okay, triangle has this. So it's an equilateral triangle. We have 3 points. I don't know, 1, 2, 3. We have seen that yesterday, so I will go fast on that. We spend more time on the other one that is a bit more complex. And this is called the D3 group. So in the D3 group, okay, those distances are the same, and you have some rotation axis. I mean, you actually have you have 4 rotation axes. You have a rotation axis here. It's a 3-fold rotation. So you could go from here to here. So let's say clockwise. You can go anti-clockwise. You can go twice also. You can bring this guy all the way there. Okay. Then you also have the C2 symmetry, but around this axis. Okay, you can rotate this way. You can rotate this way. You can rotate this way. So in total, you have how many transformations? I would say 6. Yeah. So we have the identity, always. That's actually very important, especially when you're going to build character tables. So we always the identity. The transformation that doesn't do anything, basically. Or that transform the points into themselves. Then we said two C3 rotation around the origin, so 1 and 2. And we have 3 rotations around the 3 axes. Okay. So what we say, so we have 6 transformations. So we see that D3 is a group of order 6, and it possesses what we call 3 classes. So that is super important. The classes is very, very important. So this is what I was mentioning previously. Because it turned out that the number of classes is equal to the number of irreducible representations, which is called IREP for the familiar. with that. So those three classes, let me see. I will actually come back to the classes in a moment to show how things work. Now, if you, the objective of today's lecture is to go all the way to building this kind of table. So I'm just throwing it at you right now. What is interesting for us, as I was mentioning yesterday, is the combination of these invariants. Okay, we're going to combine those invariants to get some response function. Now you see that those invariants are classified. Okay, they're classified on what we call irreducible representation. We're going to see where they are coming from. And at the moment, we're going to focus on just this part of the table, understand what are those numbers. So here you can retrieve the identity. You can see you have two C3 rotation around the perpendicular axis. So this is one class, second class, and third class of transformations. Okay? So these are classes. And what you see that we have three classes, three irreducible representations. Okay? Now we're going to see what this means here. Perhaps let's do another example, a bit more fun. So what transformations do we have? Easiest one. What is the easiest one? Identity. Okay, so we have the identity. Yes. Okay, good. Then what? So it's a cubic. It's a TD. You have actually seen that, I think, Sato, in one of your presentation probably 2 days ago, you mentioned this kind of cubic crystals, okay, on tetrahedral environment. So that's, of course, a very important one. Well, then you have, yeah, okay, like 20. No, it's 27. No, it's not. No. No, I think it's 48. Or is it? No, it's fine. It's 24. So we have the identity. We have three C3 rotation. No, 8 C3 rotation on the 1-1-1 direction. So I take a corner here. Okay, and you see that from this point of view, you have a triangle here. You have the BDC triangle. You see that? So I can rotate this triangle by a 3-4 rotation around this axis that goes from this point to this point, which is the 1-1-1 axis. Okay? So I have one axis, but because I have a tetrahedron, so tetrahedron is typically 4 triangles. So I have something like that, and I have another one here. Okay, 1, 2, 3, 4 triangles. So I have 4. I have 4 axes. So I have 1. I have a rotation one way and the other way. So per axis, I have 2 rotations. Okay, I have this one and I have this one, and I have 4 axes. So I have 8 rotation. I have, let's say, I have a rotation around the z-axis. I can bring this guy here and this guy here. So it's a C2 rotation. I can bring that here and this one here around this axis. Okay. So now I have, let me see. I have, in this case, 3 equivalent axes, x, y, and z. So you have 3 C2 rotation. I have, so the sigma d reflection. So sigma is a reflection, and d mean that it's on the diagonal plane. So, so if I cut here, for example, take a plane and I cut, I don't know if you see, I cut here through the middle. That would be this axis here. Okay. Then I have a reflection between this point and this point. These points are in the mirror plane. Okay. And again, I have 6 of them. Because I have 6 faces. And then there is some improper rotation, so rotation plus mirror. So those ones actually they are 4-fold because I can bring Let me see, how does it work? Yeah, I can bring this guy here and make a mirror symmetry and bring it here. Okay? I rotate and then I invert. So if I rotate this way, I will have something like that. And then I invert it. So I'll actually go back to here. Rotation plus invert, plus it's not an inversion, so it's a mirror symmetry. So we have 24, so the order of the group is 24, and you see that it possesses 5 different classes. Okay? So if I look at the character table, again, I have 4 classes, 4 what we call irreducible representation. We'll see what it is. And now you see that the invariant functions that are associated to each of those representations are different from the previous one, of course. Okay? And then we have much more numbers inside. We'll see what those numbers mean. So, do you guys have any questions at this stage? Yeah.
What about the inversion with respect to the origin?
There's no inversion here. Because if you take this guy and invert it, he's going to go here, and there's no point here.
Ah.
There's a mirror. Okay. So now what we're gonna do is introduce what we call a representation. So no, I'm not exactly following Dresden House because I'm going the other way around. I will start with the easy one because the other one is much more abstract, so I have a very hard time to understand it. So we're going to start with the easy one. If I ask you to represent these transformations spontaneously, you're going to write a matrix. Now, because we condensed matter physicists, so we don't really deal with points, we deal with vectors. Right? So I take a vector and I'm going to transform my vector using, I don't know, reflection, rotation, all this stuff. So here you see the transformation that, actually these are the same transformation that we saw yesterday on the D3 triangle that Oleg presented. Okay, you can, so that the identity keep the 1, 2, and 3 points at the same place. So A and B are the two C2 rotation. So the A means that you rotate this way. No, sorry, A, B, and C, excuse me. There are 3 C2 rotations. So one is this one, that's the A rotation. B keeps 2 unchanged, so exchange 3 and 1. And C exchanges 2 and 1. Okay? Going step by step, very slowly, which is good for me because otherwise I get lost. And then we have the 2 C3 rotations that, rotate the points either clockwise or anti-clockwise. Okay? So that's what I'm considering the points. Now, if I want to take a vector in the xy plane, I can apply those symmetries to my vectors, and I will write everything as in terms of matrices. So I take a vector xy. If I do not transform anything, I keep xy, so that I will have a diagonal matrix. It's a 2x2 matrix because I'm considering the xy component. I'm not considering the z component yet. Okay, we'll see that later. And then you can verify that A, B, C, and D are matrices, are rotation matrices. Okay? So this is what we call a representation, because we represent the abstract transformation. So it's very important to keep track of what is an abstract object and what is a concrete object. Okay, a representation is, the way we do it is, it's actually, well, it's not a representation yet actually, it's actually a matrix representation of our transformation. So the transformation is an abstract concept. I'm transforming in a certain manner. Now, how am I going to transform my vector? So here I said, yeah, let's move up. Here I said, I'm using this, I'm using this frame, the XY frame, and I'm going to have those matrices. But what if I'm using this frame? the transformation themselves have not changed. I am still exchanging points, I'm still rotating this way and so on. But if I want to express it in a mathematical language, yeah, I should actually have put the axis here, by the way, because this is not even orthogonal, sorry. My bad, I will correct that. So let's say I can take this one, I can also take this one. Then of course my matrices will change. That is super important, because it means that the way you represent a transformation is not unique. The transformation is unique. It is very clear. I'm going from 1 to 2 to 3 and so on. But the way I represent it is not unique. Which is kind of an issue, because here it's a very simple equilateral triangle, but imagine what we do with the tetragonal point group that we had previously, or even more complex point group. In this case, well, choosing a representation will be completely arbitrary. It's up to you. And that is not good. If you want to make a general theory, it's pretty bad. So it doesn't matter, because the good thing is that, and this is something we're going to see in a minute, there is one thing that is unique to all those representations, which is, sorry? No, I'm sorry. Let me be more concrete. Yeah, I heard that. You said, right? The trace? That's fine. No? Who said that? The trace? Yes, okay. So you take a matrix, the thing that you can, if you have a certain matrix A, as I said, you can write this matrix. I mean, you can, the A matrix will be in the, let's say, the blue frame, and if you actually rotate this blue matrix into the red frame, and then you're going to have this matrix. Now, of course, this is not unique, but the trace is unique, actually. The trace is unique because the trace of that is the same as the trace of A. And that is super important. So this is the small points, the small characters that you have in the table are the trace of the representation, of the matrix representation. So that's for the two-dimensional vector. Now, I haven't talked about what happens for, actually I have two other mathematical objects that I could transform through that. I have, well, the other component, and I also have the scatter. The scatter is very easy because scatter doesn't transform, right? It's a scatter, so you can rotate the scatter, it's still a scatter. So it's like the identity. This is the easiest thing. So to understand where this, I mean, how the Z part transforms, and why we actually have this other representation, I don't know how we'll do that. Let me think. Yeah, okay, that's abstract. So let me actually not do that. I will do something simpler. So we have done the X and the Y. Now let's do the Z. Okay? So A, B, C, D, F. The question is, I'm taking, if I take a constant number, then of course, none of those transformations impact the constant number. Okay? So it means that the trace of the representation will be the same everywhere. I'm going to come back to that, but this very boring line is present to absolutely every character table, and it's very important to construct it. So this I don't really care. I mean, it will be important if you consider energies, for example, because energies are typically not affected by any of the transformations, because they fulfill the symmetry of the system. This is the Neumann's principle. So they should be under this particular representation here. Let's take the Z component. If I take a Z component here, then how does it transform upon the identity? Well, in itself, right? Easy. Now, what about the A, B, and C transformations? So the A, B, C transformations, you see there are rotations like that, out of the plane. So I take Z, I rotate, I'm going to have minus Z. Okay, so I'm getting minus z, minus z, minus z. And then if I rotate in the plane, I have z. Okay? So basically now, what I have done, that I have transformed the scatter, the z component, and the xy component with all those different matrices that I have mentioned. Okay? So, okay, well here it's, the book has a much more mathematical representation of this, a mathematical derivation of this representation, but it doesn't really matter. What matters for us is the fact that the EDF leave the Z invariant and the ABC just gives a minus. Now, if I put everything together, what I have is something like that. Okay, so that's one particular representation. So in one-dimensional scatter, it's 1 everywhere. In the Z component, it's 1 minus 1 minus 1, 1, 1, because it's one-dimensional also. So you have two one-dimensional representation, and I have one two-dimensional representation. And with those three representations, I represent. It's redundant, I apologize. My English is not good enough. I represent all the possible ways to transform objects using those symmetries, okay? But the way I'm writing things here is not, I mean, here it's rather unique, but here, as I said, this is not unique because it depends on the frame. Actually, even that is not unique. Because instead of, I'm taking, well, because I'm taking the axis perpendicular to the plane, but if I take it, you know, if I completely change my frame, then I can imagine that I could have something different. So, I could also, here you see I have only two one-dimensional and one two-dimensional representation. But you can tell me, yeah, but what happens if I have a much more complex vector? Yeah.
So, just for curiosity, can we have also another kind of mathematical object, like maybe polynomial or something?
Yeah, absolutely. That is a very good point. Okay, I thought that you were asking about higher dimensional object. So I would say both ways. So higher dimensional object and definitely non-linear object, because here I'm just taking x, y, and z because this is easier for us to visualize how things are working. But the same representation apply if you have polynomials. And that's the whole point. We'll see that in a few slides how this applies to polynomials. And actually it only applies to certain types of polynomials which are called invariants. That's the key. That's where invariants are coming from. So now imagine that we have a multi-dimensional vector to deal with. Then in this case, here I'm just showing it's a four-dimensional vector. It turns out that I can build any representation of higher dimensional vector. So here I'm just taking a four-dimensional vector. In terms of those three representations. So this kind of representation is called the reducible representation. It's really like vectorial space, okay? I'm not doing much math here, but you can picture it, you know, we're actually dealing with a frame with ortho, you know, you're very familiar with X, Y, Z. What we actually have here is what we call gamma 1 prime, and gamma 2. We actually have a space of representations. It's a frame of, it's a basis of representation. And that's the whole idea behind the representation theory, is that you can take any, what we call general representation of the system, any general higher dimensional vector, high dimensional object, and actually parse it, decompose it in the minimal representations, which are called the irreducible representation. So this one is called the reducible representation. This one is called the irreducible representation. So mathematically, we can write that the representation in 4 dimensions will be gamma 1 plus gamma 1 prime plus gamma 2. 1 dimension, 2 dimension, I have a 4-dimensional object. exactly like if you write a general vector in a frame, in a three-dimensional frame. You would say that, I don't know, V will be alpha x plus beta y plus gamma z, where in this case, gamma r is gamma 1 plus gamma 1 prime plus gamma 2. So you can also understand why you need a thick book to explain that. There is a correspondence, but of course, these are not simple vectorial spaces, okay? They are much more complex things, so you need a lot of mathematical concept behind it, and I'm completely skipping everything. Now, before moving on, just for fun, I'd like to introduce you to the Schur's lemma. You remember what Barry was mentioning yesterday? Okay, this is the actual Schur's lemma. Would you appreciate it? Super concept, you know, it's very, very abstract. And actually those lemmas, of course I didn't give you any introduction or development and everything. This is just the lemma that you find in the book. It turned out that these extremely technical lemmas are at the basis of the representation theory, because what they actually imply is that you can represent any symmetry group in terms of what we call irreducible representation. Exactly the stuff I mentioned here. Okay, so this idea about decomposing a reducible representation into irreducible ones is based on these lemmas. So you can forget about that now. Just know that they exist. This is the mathematical, the more formal definition of what is a reducible representation and what is an irreducible representation. Let me see. We actually have seen a very concrete example of the decomposition between reducible to irreducible representation in Satoru's presentation 2 days ago. So you remember that he was talking about was the lattice distortion, right? Going from cubic to tetrahedral, I think, right? So you go for a cubic crystal, you have a certain number of representations there. Now, if you actually start distorting your cubic crystal into a tetrahedral one, then the representation you had at the origin are not valid anymore. They exist, right? I mean, you basically have, you still have your d orbitals, okay? But your d orbitals will not be, the degeneracy of your d orbital will not be the same. So concretely, if you take a cube, you have the full degeneracy between the 5 d orbitals. No, it's not full degeneracy, right? You have the EGT2G, right? So you have dxy, dyz, dzx, and you have the dx squared minus y squared and dz squared, okay? So these are two different representations. So it's a three-dimensional representation, it's a two-dimensional representation. So you have 3-fold degeneracy, 2-fold degeneracy. Now you distort your cubic crystal, and I don't remember, so I have to think. Those guys will be lifted, right? And here, those guys will remain degenerate, and this guy will be lifted. You can just tell by looking at the symmetry of the system. So then you end up with those guys this way, and this guy will be lifted. So you go from, so the way it works is that this is the irreducible representation, called irrep, of your cubic crystal. When you go for tetragonal, then this irrep in the tetragonal crystal becomes a reducible representation. This is reducible, and we have to project them, to decompose them over the irreducible representation of your tetragonal crystal. Okay? Okay, now I come back to the, so my objective of this first session is to build this character table, okay, this table that tells you about the symmetries and how representations are organized. And as I said, so we mentioned that when it comes to matrices, we don't have a unique representation, a unique way to write a matrix of a certain transformation. there are different ways because you can always rotate the frame. So to do that, the thing is that if you take one particular crystal, of course the symmetry property of the crystal should not depend on the frame. So to make these properties frame independent, we do not use the matrices. We represent the matrix with their character, which is the trace. Okay? And the trace have actually many interesting properties. I'm just going to point to 3 of them. The first one is the unitarity. So it's always possible. You have to trust me here. I'm not demonstration. Huh? So it's always possible to write your transformation in terms of a unitary matrix. Okay, that makes life much easier. So it's always possible. Second thing, and that is really super important, there is what is called the wonderful orthogonality theorem, which is, it actually comes back to this idea, okay, to this correspondence between vectorial space and representation theory, which is the fact that those guys are in fact orthogonal. Okay? They need to be orthogonal, they need to have no overlap, otherwise I will not be able to uniquely decompose a reducible representation on a space of irreducible representations. Right? So it means that those guys are orthogonal, and the way you can mathematically translate it is through this orthogonality theorem that deals with the orthogonality of the matrix representation of a given representation. Okay, so it's quite dense, but let me go through that. So D here is the matrix element. So you remember that we had the rotation matrices. So the D is a rotation matrix of a concrete. Yeah, maybe I can do that. Let me write it here. I'm just going to take 2 matrices, so it would be much easier. I take E on A. So we said E is the identity. So in 2 dimensions, the matrix is like that. This guy is the rotation around the, let's say, the vertical axis. And what we have is something, I think, like that, right? I'm just taking those 2. Of course, we have all the others, but it doesn't matter. So D is that. This is AD. This is the matrix representation of this particular. Yeah, it's actually no, sorry. This is actually the. I'm going to call it the gamma 2 representation. Right? It's a gamma 2 representation. So it's the matrix of transformation E in the representation gamma 2. Because I could also have the matrix of transformation E in gamma 1. What is that? It's 1. Okay, the matrix of gamma 1 prime of transformation A is, if you remember, -1. Switch my z vector. Okay, so this is what this guy means. This one here is just a matrix element. 1, 1, 1, 2, 2, and so on. And what this orthogonality theorem says is that because those representations are orthogonal to each other, they're completely separate. I can decompose any irreducible representation into those irreducible representations. Then I have this big formula. So D is the matrix, gamma J in this is the irreducible representation, R is the symmetry operation. H here is the number of elements in the group. So in the D3, H equals 6. In TD, H equals 24, and so on and so forth. Okay? And this guy here is the dimensionality of the representation. So the dimensionality of gamma 2 is 2. Right? You have 2 dimensions here. So I don't expect you guys to remember everything, of course, but you know, let's walk slowly through everything. Let me see. Yeah, so yeah, and as I said, what is interesting is that we're gonna focus essentially on the character. So we are actually not going to use that. Okay, this is a very important theorem, but we're not going to use this version of the theorem. Because as I said, this matrix is not unique. So this is fine, but it means that, okay, if we can find something a bit simpler to deal with, it will make our life easier, and we're actually going to use the version of this orthogonality theorem applied on the characters, not on the matrix. Because now the character is unique. So concretely, this is my my table, as I was mentioning, gamma 1, gamma 1 prime, gamma 2. And I'm just going to replace all those numbers by the character. So the trace here, so I'm going to have a 2 here, 0, 0, 0, minus 1, minus 1. And of course, in one dimension, the character is equal to the matrix, because it's one dimension. So I end up with that. Okay. So that's what those numbers mean. And what is super important for us is that the series of characters here is unique to a representation. Now, this is unique. It doesn't depend on the frame. Any questions? Okay. So now we're going to build a character table. And for that,